Hi everyone, I welcome you all in the next lecture of quantum mechanics. So in previous lecture, we have seen the criteria for the wave function, whether the wave function is acceptable or unacceptable in the quantum mechanics. And also we have seen the criteria for the normalization of wave function. In today's lecture, we will see the one of the most important problem in quantum mechanics that is called as the particle in a one-dimensional infinite potential box that is also called as the infinite square wave problem. So in this system, what happens? A particle is, confined between two infinitely high walls that you can see here on the screen. So these are the two infinitely high walls. So the particle can move here along x direction in 1D, right? So that is the assumptions for this particular problem. That's why this is called as the particle in 1D box, where the particle is allowed to move along x direction in one dimension only, right? So here you can see that the particles are, two infinitely high walls are there, and the particle is trapped between these two boundaries. So I have divided this, system in three different regions. There is a region one where the potential is infinite, region two where the potential is zero, and the region three where potential is again finite. So so the important point is that the particle can only, exist in region two, because region one and region three corresponds to, infinite potential barrier. So in region two, the potential energy is zero. That means V is equals to zero. So the particle behaves like a free particle inside the box. And if we see the Schrodinger equation where it is equals to E psi of xt, that is equals to minus h cut square by 2m del 2 psi by del x square plus Vx psi of xt. So we are interested in solving this problem in region 2 where the potential is 0. So E of psi xt that will be equals to, the Schrodinger equation. In Schrodinger equation, you will have to substitute the value of V is equals to 0, and then you will see this Schrodinger equation will get converted into of this form. And finally, once you rearrange the parameters and, in this way, then you will be getting a second order, ordinary differential equation of the order of del 2 psi of ht del x square plus 2me by h cut square psi of x that is equals to 0. So this basically looks like a problem like d2y by dx square plus, m square y equals to 0, where m square or k square is equals to 2me by h cut square, something like that. Okay, great. So from classical mechanics, the kinetic energy of a free particle can be written as like E equals to p square by 2m, where p is equals to, linear momentum and m is the mass of the particle. And from the Broglie hypothesis, we know that E equals to h cut and k. And from here, we can substitute this kinetic energy thing, E, and we will be getting the value of hk square equals to 2me. And once we substitute these things, you will be getting the value of k square that is equals to 2me divided by h cut square. And in above equation here, in ordinary differential equation, we see there is a parameter that is 2me by h cut square. And we can replace this value 2me by h cut square with k square. And then this equation will be a symmetrical, second order ordinary differential equation. And this can be solved using boundary condition. So here boundary condition can be like x equals to 0 and x equals to s. These are the two boundary where the probability of finding of the particle is 0. The particle cannot be found at x equals to 0 and x equals to a. So we will use these two boundary conditions to solve this ordinary differential equation of the second order, and we will calculate the value of psi. So let's see how we can solve this thing. So once we solve that, we will be getting the equation like psi of x that is equals to a e to the power k1x plus p e to the power k2x. Here in this problem, k1 and k2 equals to k, something like that. And from complex number, we know that e to the power I theta that can be written as cos theta plus iota sin theta. And then we can extend this psi in this form that psi x can be written as now a sin kx plus b cos kx. Now this is complete wave function, which is a function of x. Now we can substitute the boundary condition that we have seen earlier. And once we substitute the boundary condition, we can calculate the value of a and b. And from there, we can get the eigenfunction. And the eigenfunction that we will get here, that will be the discrete eigenfunction that we will see later on. So once we substitute the first boundary condition that the value of wave function psi at x equals to 0 is 0. And once we substitute these things, we will be getting the value b that is equals to 0. And once we get the value b0, that is that will give you the value of wave function psi, that is equals to a sine kx, and that is the eigenfunction, and which is a sinusoidal in nature, right? Now, once we substitute the second boundary condition here, when psi at x equals to a, that is equals to 0. So here we will be getting that 0 equals to a sine kx, ka. And from there, we can calculate the value of k, that is equals to n pi by a. So this is a discrete eigenvalue where that will depend upon the value of n, which the value of n can take from value 1, 2, 3, so on and so forth. Now, once we get these things, we can calculate the value of k square a square, that is equals to n square pi square, because we want to calculate the energy, right? And we'll see how we can calculate the energy over here. And from here, you can calculate these things, 2me upon h cut square a square, that is equals to n square pi square from the previous slide. And finally, we can get this value of energy, that is En, that is the quantized energy, En, that is equals to n square pi square h cut square divided by 2ma square. So h cut is h by 2 pi, that is Planck constant by 2 pi. We know the value of A is the width of the box, right? M is the mass of the particle, n is the value of n can take from the integer, that is 1, 2, 3, and so forth. So from here we got the value of energy, that is En, that is directly proportional to the n square, right? So now, so from here you can see that we have got the value of psi, that is equals to a sine n pi by a x. Okay, and from here we have got the quantized energy, that is En, that is n square pi square h cut square divided by 2ma square. And once we plot this quantized form of energy over the energy diagram, you can see that we can plot like ground state energy E1, first excited state energy E2, that will depend upon the value of n. When n equals to 1, that is the ground state energy, that is E1, that is equals to n square h cut pi square h cut square by 2ma square. E2, when n equals to 2, that is called as the first excited state. E3, that is called as the second excited state. E4 is called as the third excited state. And you can generalize the energy diagram like En equals to n square into E1, where n is equals to 1, 2, 3, so on and so forth. So this is basically the discrete energy level in the quantum mechanics, right? So we have till now we have calculated the discrete energy level of the particle in 1D box, where the motion of the particle is constant along the x direction only in 1D. Now, moving towards the next part where we can calculate the constant for the eigenfunction. So here we have seen that this one is the eigenfunction psi x, that is the wave function a sine n pi by a into x. So where capital E is the constant, and we have to calculate this constant as well. So how we can calculate this constant? So we'll use the property of the wave function, that is the normalization that we have seen in the earlier lecture. So once we do the normalization, and this value of a can be calculated using the normalization of the wave function, like if you integrate the wave function from minus infinity to infinity in the domain, and the complex conjugate of wave function, that is psi star and psi, that will give you the value 1. So here the domain of x is 0 to a, that's why we'll integrate this wave function between the domain 0 to a square, and that is sine square kx dx, that is equals to 1. So here we have to use some calculus and trigonometric formula, and we can finally calculate this integration like this. We have multiplied and divided by 2 over here on the screen. And once we use 2 sine square kx, trigonometric identity is like 1 minus cos 2x, and then we can perform this integration in the limit of 0 to a, and we will be getting the value of mod of a square by 2, a, that is 1. So from here we can calculate the value of a, that is equals to root 2 by a. This is simple mathematics where we have used some trigonometric and calculus formula to calculate the value of constant a. Once we get the value of a, we can easily write the wave function, that is root 2 by a sine n pi by ax. This is the quantized wave function as well, because the value of wave function will depend upon the value of n, because our eigenfunction is the discrete eigenfunction. Okay, so from here we can also write this transient wave function also, that when I was driving the Schrodinger equation, there I have told you we can multiply using the wave function of the time varying part, that is e to the power minus I omega t, and this will give you the complete wave function that will depend upon the value of x as well as the t, right? So this is called as the time dependent wave function also. So till now, we have calculated or we have derived the wave function which vary, with respect to x and time, and also this vary with respect to n. Okay. So now coming to the one of the most important theories or concept for the the particle in one-dimensional box, that is eigenfunction and the quantum state in the particle in a box system. So here we can see that as we got the normalized wave function in this form, and